So today's Python video is actually not going to be on Python, it's going to be on a programming language called Solidity, which actually is partly based on Python. And actually I've already Googled Solidity programming here so we can see it. And just as the overview at the top here, I'll kind of like zoom in for a little bit and then maybe zoom back out. But if we look at this top corner over here, it says Solidity is an object-oriented programming language for implementing smart contracts on various blockchains, most notably Ethereum. Solidity is licensed under the GNU public license and so forth. Implementation language C++. We'll go and have a little deeper look into that. So let's just kind of zoom back out again if we can and click into Solidity. And actually, you'll see that I had a little cheat open. I did actually open up this remix thing on a link, but I literally haven't looked at anything in this, and I've probably looked at this website for about 2 minutes. So everything here is a completely new look, and I'm just going to literally investigate to see what Solidity is and kind of like how it can be used and so forth. So let's just read some of the documentation, I guess. But as a first starter, it's got over here that Solidity is a statically typed curly braces programming language designed for developing smart contracts that run on Ethereum. I guess I could click on this Ethereum thing and open up a new link. Welcome to Ethereum. Ethereum's a cryptocurrency effectively, and there's a whole bunch of things that can be done with Ethereum. Solidity is effectively the smart contract programming language for that. So let's take a further look then going into it. Solidity is evolving rapidly. We aim for regular non-breaking releases every month. Okay, so I guess new versions basically every month, but it seems like they'll probably be backward compatible with approximately one breaking release per year. So I'm not 100% sure what a breaking release is, but maybe we can Google up actually what breaking release is. It's something. What is a non-breaking release and what is a breaking release? So search for Google breaking release. Desperate for money, okay, so we get all of these IMDb things and everything else because the film is obviously called Breaking Release. So breaking release programming. Right, maybe if I do that. Okay, breaking change. A change in one part of the software that potentially causes other components. Okay, so it is something basically that I'm going to say maybe not. I use the word backward compatible, and that's what it might be. It might cause some breaks somewhere, whereas there'll be other advancements that won't cause breaks. They won't cause things to break down. Okay, so it's a language that's effectively developing. You can contribute to Solidity. Solidity continues to improve with the help from all our global community. Check out these ways to get involved and contribute with the Solidity project. So you can start contributing. I won't click on that link because we're really learning before we can contribute anyway at this stage. Stay updated with the Solidity blog. That's going to be up here anyway, but it looks like there's a Solidity blog there. You can see the upcoming changes for the next breaking release by switching from the default branch to the breaking branch. Okay. You can actively shape Solidity providing your input and so forth. So we won't read any of the other announcements because they'll be probably for like already using Solidity users. Here's this Hello World program. So, and the ERC20 is the type of contract. But anyway, this is Hello World. I'm not sure if this can be run because there's no run button here. Is there a run button anywhere? Nope. But I did open up in a tab. I should kind of like show where it is, so I'll get there anyway. But there's something called Remix, which looks like an editor in some way. And when I didn't have this license, if I kind of like delete that, it has this little yellow warning sign saying Pragma Directive. It's expecting some Pragma Directive, I guess, or something. So I'll do a Control Z if I can, and it puts it back. And I was just reading about it. We're going to read about all of these things, I guess, at least, because I was like, oh, let's have a little figure out as to how all of this works. So, but how do you run this code? Because there isn't. Can I do Control Return to run? No, it doesn't do anything in particular. So, but at least this is what Hello World might look like in Solidity. And I already know because the only thing I did read was that this pragma Solidity, and well, this line needs to be there. It's kind of like, you know, the license that it's under, so you always have to have that at the top. And then this one's telling you what version it's compatible for. So this one, I believe it's greater for, it's compatible for all versions above 8.0 and above. And you'll see that. I'm just going to imagine that, have we defined a contract here? And then inside of the contract, we've created a function which is hello world, and it returns hello world. So we call it a function and it's called hello world. Public pure returns string memory. I guess it returns the string of hello world, but I don't know how it's called at this point in time. You know, I'd guess that, you know, something like you're going to do a hello world here. I presume that you'd be doing it inside the contract, like you'd call that and ends with the closing brackets and a colon like that. I imagine that's C++ syntax. Anyway, we'll ignore this for a minute, I guess. Compiler result. The thing is, it comes out with a compiler result here. Is there a hello world at the bottom or something? Nope. Okay, we'll see anyway. So let's scroll back up. We've got the blog up here, and then we've got documentation. So again, this is about a new release. We're excited to announce the latest release. I'll zoom in a little bit actually, because then it's easier to read the code. So we're excited to announce the latest release of the Solidity compiler. So this is the newest version, I guess. And that was given out in July 19th, 2023, so not long ago, like a week ago, basically. Notable new features: stacked in-memory movers, always enable via IR, and so forth. Okay, so this is new features, but again, we don't know what any of the features are, so we're not going to go into new features. We then go into the documentation to have a look at what's in the docs, because this is quite, usually the docs tell you a lot. If they're written well, the docs are very helpful. So I'm going to zoom in again on the docs. Let's go and zoom in a little bit more even. We've got our little, I guess, an introduction to smart contracts and so forth, but it looks like this is the top of the documentation anyway. So I wonder if I did go there. Okay, we'll go back because I don't want to do that too early. Documentation, because I would imagine that all of these are what comes down here, but we've got getting started. Is there even a getting started bit there? No. No. Okay, so let's just read the documentation on as it is from the top downwards. Solidity, which is this programming language, which is not Python. Solidity is an object-oriented high-level language for implementing smart contracts. We read that before. Smart contracts are programs that govern the behavior of accounts with the Ethereum state. Ethereum is a cryptocurrency. Ethereum is this. So let's continue. Solidity is a curly bracket language. Curly bracket language is a language that looks like C++ in a way, or JavaScript. We can sort of like, we'll open it in a new tab. I don't know if it would have opened in a new tab. But curly bracket languages are most languages actually. So Python is not a curly bracket language. Python uses white space. So curly bracket program that have a syntax that defines, basically what it is, it has a syntax that defines block statements inside the curly braces. So and these are the curly braces. So your block of code goes inside this curly brace basically. The syntax was originated by BCPL. I'm not even sure what that is, but it's a long time ago. Procedural program. BCPL is a procedural, imperative, and structured programming language. Anyway, it was originally the B language before it became C, and was popularized by C. Many curly bracket languages descend from or are strongly influenced by C. So C++ is a derivative of C. Python is a different fork or branch of C to C++ in a way. And Python actually is C, is one of the things it has is C without the curly braces and without the semicolons at the end of the line. So other languages that we might see here, if I just jump to, I was going to jump to JavaScript, Sonny, but it'll be we've got Java, but I don't see JavaScript. Finally, oh, there we go, JavaScript, TypeScript. Um, and I don't see Node, but Node.js will be the same, which is the back end of JavaScript. So, and all of these other languages that are there as well. Funnily enough, there's a D and an E, so there was probably an A language as well, I imagine. There's B, there's C, which was developed in 1970 by Bell Labs. Python came out in 1991, so some 21 years later after that. Then there's D, then there's E and stuff. There's a whole bunch of other languages. Swift as well is there. I think another popular language is Kotlin. Is there a K here somewhere? Yeah, there we go. Anyway, a whole bunch of languages. More languages are not actually curly brace languages. So I guess, is there anything interesting to say beyond that? No. So we close that out. It's a curly brace language designed to target the Ethereum virtual machine. Right. It is influenced by C++, Python, and JavaScript. That's quite interesting because it's the mix of the languages that, I don't know, like in data science and heavy computation, data science, and the web are encompassed by, a mix of these languages to various degrees. So you can find more details about which languages Solidity has been inspired by in the language influences section. So there's a little section here. In the early day, okay, let's have a little look at this because it looks quite interesting. Although we will jump back. Language influences. Solidity is curly brace, most profoundly influenced by C++, but has also borrowed concepts from languages like Python, JavaScript, and others. So we'll see where that is because the syntax is very much C++-like. The influence from C++ can be seen in the syntax for variable declarations. For loops, because a for loop, actually I did have a glance at a for loop because I tried to do one. In fact, I tried to do a for loop. One of the first things I ever tried to do in most languages is sort of like, here we go. Here is an example. Where is it? Yeah, I just typed in for loop in Solidity. It says here is an example of how to do a for loop in Solidity. I'm like, what the hell does all of this mean? I'll copy and paste it into some editor. But one thing that we do notice in the for loop is this syntax over here that is very much a C++ and JavaScript type of thing, where we do the for and then everything in here is the looping criteria, where we start from. I equals 0, where we end with, so I equals numbers.length, so like some length of an array, and the incrementation operator, so how many to jump, where I++ means 1. So we're starting from 0, going to number length, incrementing by 1, and doing whatever we want to inside our block of code, which is inside the curly braces. And when we finish our commands, not including the curly braces, we finish our regular lines, we use a semicolon so that we know that there's a line, and that's typical of all curly brace languages. So the influences come from the variable declarations, for loops, and the concept of overloading functions, implicit and explicit type conversions, and many other details. In the early days of the language, Solidity used to be partly influenced by JavaScript. We'll see why. I guess this was due to function level scoping of variables and the use of the keyword var. Okay, so I guess you don't, like, when you're declaring variables in JavaScript, you don't do like string or something, you do var and let, and then it like type ins afterwards. So the JavaScript influence was reduced starting from version 0.4, and now we're on 0.8, so 4 versions back. Now the remaining similarity to JavaScript is that functions are defined using the keyword function. So, and we kind of like saw that in this little thing over here where we had this keyword function. So this is the definition of a function. In Python it's def. I can't remember even what it is in C++. I think it's probably also function. Or maybe it's not. No, it's like it's int or void or something. You declare it with its type. So in JavaScript it's function. Solidity also supports import syntax and semantics that are similar to those available in JavaScript. Well, that's quite nice to know. It's quite convenient. both JavaScript and Python have easy import syntax. So you can create a little script. The Python version of import, you don't have to export things or make them public. Literally, you can see everything. So all you have to do is import the module. The JavaScript version is you create your module, which is basically your file, and then you do something like module.exports, and you say everything that you want to export out, whether it's a function or a variable. Besides those points, Solidity looks like most other curly-braced languages and has no major JavaScript influence anymore. So, okay, basically it's down to this keyword here, and importing. Another influence to Solidity was Python. Solidity's modifiers were added trying to model Python's decorators with a much more restricted functionality. I'm not a huge fan of the Python decorator, although it's convenient. It's referred to as syntactic sugar, which is basically something that you can do in code without it needing to be there. So you don't really need a decorator, but the decorator is sort of like cute and convenient. A decorator is something that effectively goes above a function, like the line above a function in Python, and it gives the function some additional capabilities more than it had before. Prior to decorators, you would just wrap your function into a wrapper function or something. Furthermore, multiple inheritance, C3 linearization, and the super keyword are taken from Python. So this is referring to classes, I guess. And I think the super keyword is when you take the variables, is it from the parent class? I believe it's that way around. So that's what this super keyword is taken from Python, as well as a general assignments and copy semantics of value and reference types. Okay, I'm having a little think about that, because reference types, Python uses a reference counter for clearing its variables, basically, so for memory management effectively. So possibly it's taken that from there as well. Okay, let's have a look. Solidity brand guide. Solidity programming is open source. That's good to know. Governed by a core team. The core team is sponsored by the Ethereum Foundation. So, Solidity should be used to refer to the Solidity programming language solely. Please do not use Solidity. What is the difference between this and that? Why does it say please do not use Solidity? Oh, please do not use Solidity to refer to any other programming language. Well, I guess you wouldn't, because it isn't. So, in a way that is misleading or may imply association with unrelated module, tools, or documented as resources. I'm not sure where or how one would want to do that anyway. In ways used to confuse the community as to whether the Solidity programming language is open source and free to use. Okay, fine. Well, anyway, I don't think we need to really go. Well, there's not that much further anyway. It's distributed under the Creative Commons Attribution International License. Basically, you have to share it, you should state what you're using and share and say where it's come from and all the rest of it. So that's basically that part of Solidity. So let's just go back to the documentation where we were. We were just on this language influences section, so we've seen where it's come from. It's mostly C++ by the looks of it, with a touch of JavaScript for the functions and the variable declarations and the imports, and a tiny bit of Python from the what appeared to be classes, because for example it used the super keyword, and also potentially looked like it was using the references or reference counting potentially for Python memory management. So at least that's its background. That's what it is. Solidity is statically typed, supports inheritance, libraries, and complex user-defined types, amongst other features. So the reality is it's a statically typed language, which I don't know, 50% of languages are, a huge percentage are Python statically typed. C++ is statically typed, Python isn't. Python's dynamic. Um, TypeScript is statically typed, JavaScript is dynamic. So statically typed means you declare your variables when you're effective. You declare the type of your variable as and when you're defining your variable. Whereas the dynamic languages, you can declare a variable and it kind of like it gets its type inferred. And anyway, you can overwrite them, where the statically typed language won't let you do that. Now, there's pros and cons to both of them. The statically typed languages, you would argue that they're a bit more cumbersome in a way, but that cumbersomeness gives you the peace of mind when you're writing large pieces of code that you don't accidentally overwrite something somewhere. That's what statically typing will just prevent you from doing it. So on the one hand you give up, but on the other hand you gain. You have your choice. You can go with C++, you can go with Python. In some ways these things are beginning to migrate towards each other, as in, like, think a language like Python, which you didn't have to sort of like type hint or anything. Now type hinting, and even JavaScript, there were two approaches from these dynamic type languages, where I guess one of the issues that the community would have is that when you create a variable that you could accidentally overwrite it, and sometimes you forget what the variables are, so the type hinting was introduced. Now JavaScript went down the TypeScript route, which is the statically typed version of JavaScript, and Python went to type hinting, which still treats you like an adult, should I say, because you kind of like, you can hint what the types are, but it's not binding. So anyway, that's kind of like the difference between all of that. With Solidity, you can create contracts for uses such as voting, crowdfunding, blind auctions, and multi-signature wallets. So it really is, specific for crypto contracts. With this Ethereum, it's designed for contracts. That's kind of like what was in the forefront. I guess another language could have been used, but this language is kind of bespokely, for a very well-defined section of the market. So I don't know if we'd see like, it's not a general purpose multi-programming language like Python. Let's just say that. Or at least, and it's certainly going to be a much smaller community, at least for the first few years. Will it grow to be as big as the other languages? We'll see, I guess. When deploying contracts, you should use the latest version of Solidity. Apart from exceptional cases, only the latest version receives security fixes. So, I mean, that's true for most languages, or you stick to your versions. The reality is, in every single programming language probably ever created in man, they're always going, by mankind, they're always going to have iterations and modify. C++ is on version 17. Python is on version 3.11. It had a major change from Python 2.7. That was the end of Python 2, so it went over 7 versions. Python 3 is good. That 3.11 implies that there's 11 versions in Python. In Python 3, which had major changes from Python 2. So both of these things have had like loads and loads of changes. The same for JavaScript. God knows what version JavaScript's on, but again, it would have been 20 versions down the line because improvements are made. The world changes, things need to be modified, and if these languages didn't kind of like upgrade and modify, then they would become obsolete in some way. And that's the survivability of these languages. So Solidity's got that same feature. Let's have a look. The recent version is version 8. There's some sort of warning. Solidity recent release version 8 into a lot of breaking changes. Okay, make sure that you read the full list of breaking changes. It's not applicable to us because we're just getting into it, and so this is like an overview. Ideas for improving Solidity. Okay, you can contribute some ideas. Getting started, understanding the smart contract basics. So, having not done anything before, and literally it's talking about this Remix IDE, integrated development environment, which I will click on in a minute, or I have clicked on because it's over. I'm actually going to move it here so it's next to it, which is this IDE. Okay, and I did this kind of like for loop thing here, which was written, looks like it's written inside this contract for loop. I don't know why it was called that even, but it's got a syntax, and we're going to figure out, or we're going to read what it's about and what we like, how we get started effectively with Solidity. So understanding the smart contract. If you're new to the concept of smart contracts, we recommend that you get started by digging into the introduction to smart contract section, which covers the following: a simple example of a smart contract written in Solidity, some blockchain basics, the Ethereum virtual machine. We can have a little glance over of it. Let's have a little glance over of all of the tabs. So there we go. That's a simple example smart contract. Let's open up this one as well. Open in a new tab and open in a new tab. So we've got 3 tabs to quickly glance over for section 1. What is a smart contract? A simple introduction to smart contract. A simple smart contract. Let us begin with the basic example that sets the value of a variable and exposes it for other contracts to access. It is fine if you do not understand everything right now. Well, that's fantastic, because I don't. We'll go into more details later, but let's just have a look. Knowing our kind of like past programming experience, for myself, it's most recently it's Python, but I have had experience with all of the other languages too, and this is a curly-based language based on C++, so you know, the syntax isn't too difficult, but let's have a little look at what it is. So the first thing we see is some sort of license identifier, and it does mention it here, and this is kind of like you know, the bit that I got to before I decided to make a video on it. And then it's got this pragma solidity here, and basically, like, I'm inferring, I'm sure we're going to be told about this, that pragma solidity is saying that it's greater than version 4.16 and less than version 0.90. Why is it greater than this? Well, I presume anything before that. Maybe this kind of somewhere this syntax, there wasn't backward compatibility, and it might not work for earlier versions, and also it might not work for versions after 0.9. So it's kind of like it's protecting you both ways. Now, when we code in Python, we create these virtual environments. Well, I don't, but you should. You create these virtual environments, and your code runs in a specific version of Python, and every module that you import has these versions. And if you don't want to break your code, if you want to guarantee its workingness in perpetuity, then you pip freeze, you lock all of the modules so that you get the correct version of the module, like if you ever wanted to kind of like run it on a different machine. Because again, like here in this case example, if we wanted to use, like, if at some point you had Solidity version 10, it wouldn't work. So, you know, Python's got this version, and it looks like Solidity does it this way. So basically, it's going to work within a few versions. That's quite nice. It's quite cute. It's good that it's done like that, quite frankly. So the first line tells you that the source code is licensed under the GPL version 3 machine readable license under the GPL license version 3.0. Machine readable license specifiers are important in setting where publishing the source code is the default. Okay, I mean, you know, just stick this at the top, I guess. It seems to be a little bit of a waste in my mind, because if you're going to stick it at the top of every code, then you should probably assume it. But I guess it's referring to this open source license or something like that. Machine readable license specifiers are important in a setting where publishing the source code is the default. Okay. The next line, which refers to this line, specifies that the source code is written for Solidity version 0.46 or a newer version of the language up to, but not including. So it's a bit like Python list, not including version 0.9.0. So everything up to, but not including that version. To ensure that the contract is not compatible with a new breaking compiler version where it could behave differently. So yeah, fine, fair enough. Pragmas are common instructions for compilers about how to treat the source code. Okay. Pragma 1. So let's have a little look. Open there, pragmas. Let's have a see what it says about pragmas. just stuff at the top. Okay, the pragma keyword is used to enable certain compiler features or checks. Okay, a pragma directive is always local to a source file, so you have to add the pragma to all of your files if you want to enable it in your whole project. If you import another file, the pragma from the file doc does not automatically apply to the importing. Okay, so basically every single time we've got to say what version that is applicable for. So here it's for all versions above 8.0 in the case where I kind of like got it from what was it, Claude. I was going to say Google Bard, but it's not. It's Claude. Not even a GPT. It's Claude AI. So right, I think that was that. Yeah, so that was the next line. So we've covered these two lines. Now what's the next bit? A contract in the sense of Solidity. So this is kind of like the new bit that we're looking at, is this piece here, really. So this block of code ends, if I was to get the drawing thing out, like I think I'm quite sure that most people can see this anyway, but this curly brace here matches this one down here. So this whole thing, all done by anyway, the visual indentation is the block of code that's inside this contract storage. There we go. So it's kind of like a little block of code visually if you were looking at it in that way. So the contract in the sense of Solidity is a collection of code. So its functions and data, its state, that the readers that resides at a specific address on the Ethereum blockchain. So I'm kind of like thinking in a way that this contract is a bit like, it's analogous to a Python class, because the contract actually contains functions and, well, what it's calling data here, which looks like methods and attributes inside a Python class. That's kind of like what it looks like. So and if you had, I presume if you had a second contract, it'd be like having a different class. So everything, and that word, the word for that is encapsulation. I don't know if I can write anywhere with something. I could just write, I wonder where. This was for my previous tutorial, previous video. The word that we're looking for here is encapsulation, which is something like this. Encapsulation in object-oriented programming, which is going to be applicable to Solidity. And we can see that, like here already, it's kind of like got class there, and it's got inside a class would be your methods and variables, basically. So I'm going to say initially that's my hunch, but you know, I'm sure maybe I could be wrong. Where are we on this? So we get the right pieces. That this contract basically is class-like. So anyway, let's continue. The line unit store data declares a state variable called store data of type unit. So I don't know what this unit is, but we see what it is. It's an sorry, it's not unit, it's uint, an unsigned integer of 256 bits. So again, like this is a static this static typing, which is so this is basically just an integer. So we're declaring that store data will hold an integer, and we're declaring kind of like, you know, how much size in memory it is. It's 256 bits in memory. So maybe we could have had a different type of integer size, like I don't know, an sint or something like that, a smaller integer. I don't know what the options are yet, but that's what it's inferring. And again, like in, I guess, C++, you'd have int store data. That's how it would look. In Python, you would just have store data because that's dynamic, so you wouldn't have to find the type. Although you could type hint it to something like, you know, int of a certain size. You can think of it as a single slot in a database. Okay. that you can query and alter by calling functions of the code that manages the database. So yeah, I don't know, kind of like his class like. This is pointing as a single slot in databases, because it's not even a memory address in particular, although maybe it's referring to one. I don't know, we'll see. Because when I'm told it's an unsigned integer, it's just like an integer basically that goes up to 256 bits, which is, I guess, is it, how many, what, ones and zeros is that? Is that 8 of them? It's 256 bits, 2 to the power of 8. Let's have a little check there, get the calculator out, and we'll do something like, let's clear on our calculator. Just 2. I wonder if I can do to the power of 8, just like that. 256, there you go. So it's 8, I guess, bytes, is it? Over there. 8 bytes in a bit in 250 will give you 256-bit unsigned integer. You can think of it, okay, so in this example, the contract defines set and get that can be used to modify or retrieve the value of a variable. We see set and get quite a lot. I actually see setters and getters, they're called in Python, in Python classes, where you want to keep things secret, or like where you want to keep, it's probably the wrong word to say keep things, where you want users to not modify the class itself, like the class variables itself, is you use a set and a get, and it kind of like they're the public facing things. So here we can, I presume here we can set here store data in this function. So it's probably something like simple storage dot set, and then you can set, and then you put in whatever you want to set it as, and that goes, and then store data gets assigned the value of X. That's what would actually happen. And then if you wanted to get it back, you would do get, and then whatever X was assigned to here, that's going to be in the variable stored data, which is inside this. I was going to call it a class, but it's not inside the contract. Simple storage, that's how I'm reading it, and then it would return you back that. So it uses a setter and getter. Set and get, not set and getter, set and get in Solidity. So maybe I can draw the little lines on it, but basically this is I will just click that off. So basically we set something here, so we would call this set function, we would pass in this X here, which will then go to this X here, which will then be assigned over to here. And then if we wanted to get it back, we would call this get function here, which would have already have, this was the stored data kind of like now belongs here anyway, and then it goes, let's go and get it, and it exists, and it's like return you this back somewhere to the user. I don't know where, but it's going to return it to you, return it back to the user. So that's kind of like a really, really badly drawn diagram, but with the arrows, if you did follow it as to how it works, it's how at least it's to my interpretation of how it works, or at least how the code flow looks like. So to access a member like a state variable of the current contract, you do not typically add this prefix. Okay, this is I'm going to say that this is a well, I'm not just going to say that this keyword is used in JavaScript and Node.js in classes to refer to the object itself. In Python, we commonly use the keyword. It's not even a keyword, we use a convention self in Python. In the JavaScript version of that is this, and that refers to the contract itself. So here, in your current contract, the contract is kind of like class-like, I'm going to say. Okay. You do not typically add this prefix, you don't need that, so that's dropped, I guess. You just access it directly via its name, unlike some other languages, just the languages I was just talking about then. Omitting it is not just a matter of style, it results in a completely different way to access a member, but more on this later. Okay. So I'm just wondering from reading that if this is used or not used, because it's unlike in some other languages, omitting it is not just a matter of style. Okay, yes, that's true. So, for sure, in languages like in JavaScript, in Node.js, and in Python, the this or the equivalent of this literally refers to the members of the class. Where we're told here that that's not the case, we don't need to use this, and we will still get the members of the class. And that's an interesting one because you've got members of the class, and then you've got things that are not necessarily members of the class. So how do you differentiate between the two? It's kind of like what I'm thinking, but maybe you don't need to differentiate between the two. This contract does not do much yet, apart from due to the initial infrastructure built by Ethereum, and so it doesn't do much yet. Let's have a look at the code. It doesn't do much yet, apart from allowing anyone to store a single number that is accessible by anyone in the world without a feasible way, without a way to prevent you from publishing this number. Anyone could call the set again with a different value and overwrite your number. But the number is still stored in the history of the blockchain. Later you will see how you can impose access restrictions so that you can alter the number. This is very interesting because it's like you've shared your code with the entire world in that respect until you do this imposition of restrictions. So anyone could call your function. That's okay. I guess we'll see what this kind of like. It kind of like this thing points to the outside world, this mutable database, this blockchain. I'm imagining that that's what it's doing, and so they store data, and so everyone can kind of like use a set and get on it. So okay, warning. Be careful when using Unicode text, as similar looking or even identical characters can have different code points. Such are encoded in different byte rate. I get that problem all the time, actually. It's really annoying. But 0 and 0 maybe, I don't know if they look identical. But yeah, just can't like use standard text, I guess. That was a warning anyway. All identifiers, contract names, functions, names, variables are restricted to the ASCII character set. It is possible to store UTF-8 encoded data in string variables. Look, I would just say keep it simple with that. I don't even know if functions can start, for example, here we got a function and its name is simple storage. It looks like it's using camel case. If the convention, like let's say you use the lowercase s here, or if you put a number first, would it break it? It would break it in Python, that's for sure. So there's obviously going to be those types of conventions that we need to be aware of. Okay, we'll go on, although we've got other things to look at too, because we opened up these other tabs. Subcurrency example. Let's just say we understood all of this and we kind of like get what it is. We've got a setter function, we've got a getter function, and we've got a contract. I'm going to sort of like stop calling it a class. I guess I'm going to call it a contract that contains this unit data stored, and the methods. We've got two methods here available, so that's kind of like it. And we had this little commenty thing for our GPL 3.0 license and our pragma, which needs to be in every piece of code because it tells us what versions it's compatible for. So apart from that, we're going to grow on to the next thing. And it says here is a subcurrency example. So let's see what that means. What's a subcurrency example? The following contract implements, just taking time, the following contract implements the simplest form of a cryptocurrency. The contract allows only its creator to create new coins. Different issuance schemes are possible. Anyone can send coins to each other without the need for registering a username and password. Okay, all you need is an Ethereum key pair. Okay, so again, we see this necessary. We see this necessary. Has to be there. We see this contract coin. It's kind of like necessary in the sense that everything seems to be wrapped up in this contract. We only see one contract. Are we able to do two contracts in kind of like one script, should we say? I don't know. And we see that again it uses camel case, although there's no other, it's just coin in this case. So it's capital, the first letter is capitalized. The keyword public makes variables accessible for other contracts. Okay, so that's kind of like Pythonic and VBA like. So we define something as public, you can see it outside of this contract. That's, you know, we understand what that means. And the opposite of public, I guess, is going to be private, which means that it wouldn't be accessible from other contracts. It wouldn't make variables accessible from other contracts, at least, I presume, if it was private. And then we've got a mapping here. Okay, so again, I don't know what this is exactly. Address public minter. Okay, I guess it's referring to an address. Mapping address goes. Well, I guess we're going to be told what some of these things are. Events. So these are like, all of this blue stuff here is keywords. Events allow clients to react to specific contract changes you declare. So we've declared an event here. If we declared any other events, I don't see that any other events are cleared, are created. Okay. Sent address from address to and unit amount. Okay. I presume you're just sending, or basically it's an instruction of where you're sending, the address that you're sending your crypto from, the address that you're sending it to, and the amount that you're sending. And I believe it's possibly as simple as that. And it's probably what, I don't know, could you have done it without having Solidity? Maybe, maybe not, you know, in another language, even in C++ or Python, or any other language, Java, I don't know. I guess Solidity is designed for it, so that's what it is. Constructor code. So we now have a constructor. So I was going to say, look, if this is a class, it's looking even more class-like, right? Why am I saying that? Because when we define a class in any of these other object-oriented languages, one of the things that we do is we have a constructor. And actually the constructor is usually the first thing that's run in JavaScript, in Node, in Python, and I'm sure in C++, in the languages I've most recently used, the constructor in Python is the init, which is a constructor. But I think in C++ and in JavaScript they're actually called constructor as well. But it's the first thing that's run in the class. So kind of like setting up the class, it's the initial conditions for it. So here it says here the constructor code is only run when the contract is created. So it looks like an initialization of it in the same way. And anyway, inside this constructor, it's got one thing, that is that minter is equal to message dot, is assigned the value of message dot sender. I don't see a message dot sender having been created earlier up here. So I don't necessarily know where this value is going to be coming from, at least at this point in time in the constructor, unless it's something that's called later on when you sort of like call it and construct it. Am I blind and I've missed message.send, or even message, actually, come to think of it? I guess message is part of the language because it's in blue and it looks like a keyword, so message.send must be something like that. We'll discover what that is. And also we're going to have a description down below anyway, so you know, this is just my take on it, at least to start with. But sends an amount of newly created coins to an address. Again, I guess we're seeing can only be called by the contract creator. Okay, so you meant the address receiver. Okay, so the creator is saying where it's going to, who the receiver is, and the amount that they're going to be sending. I imagine it works that way. Require message dot sender equals minter. Okay, fine. And balances of the receiver is incremented by the amount that was sent. So it kind of like looks relatively logical. Errors allow you to provide information about why the operation failed, and are returned to the caller of the function. Okay, so this is kind of like very common. How we like, I was just trying to think how we do handle errors. We've got try accepts and things like that, and accept raise and stuff like, so we can raise errors in similar ways. So here it looks like error insufficient balance. Unit requested unavailable. Okay, I don't know if there's any if there's other types of errors that can be raised, but you know, anyway, that's what it is. I don't know if this is an inbuilt function in a way, because a unit requested, I guess it checks a unit requested by the amount available, because if the amount requested is more than the amount available, then this error should get raised in some way. I'm imagining it works like that. Sends an amount of existing coins from any caller to any address. Okay, so we have one function here actually, function mint. And we've got error handling, and then but the error handling is after the function, and we've got another function here. It opens here. We've got an if statement that closes here, and that's the end of this function over here. So sends an amount of existing coins from any caller to any address, so this is what an if statement is. If, and then inside here is just a condition. So that's a standard if statement. We've seen it loads of times in loads of different languages. And then some other stuff that we potentially haven't seen, but I think it's relatively logical, which is revert insufficient balance. I don't know. It gives you the money back if the balance isn't sufficient. And it's doing some adjustments. I guess the sender will be deducted the amount and the receiver will be credited the amount. That's what this minus equals and plus equals means. Emit sender sent. So is that sending? I presume that this message.send is sending a message to the either to the sender or to the receiver. I'm imagining that's like some sort of notification. So let's read what it is, because I've blathered about it. Maybe some of the stuff that I've said is wrong. So I just kind of like, I'm just inferring what this reads like from someone who's got some background in coding, and how I might read the comments and how I might read some of the code, at least, or what it looks like to me. But let's see what it actually means. This contract introduces some new concepts. Let us go through them one by one. So here was the first thing that I didn't really know. The line address public minter, which was this line here, kind of like, what is all of that? We knew what public meant because we were told, because that was written in the contract. It makes the variables accessible from other contracts, so we know what this piece means. So it declares a state type, a state variable of type address. Okay, we can see what an address is. The address type is a 160-bit value that does not allow any arithmetic operations. It is suitable storing for addresses of contracts or a hash of the public half of the key pair belonging to the external account. So it's literally like an address. It's part of the key pair. I guess it literally links into the blockchain. So whereas when we have an address, I'm imagining this, whereas where we have an address or a pointer in C++ or a mutable type in Python, which kind of like refers to a place in the memory, this address here, this type variable address, is kind of like referring to somewhere like this type. That doesn't take any other, it's just a pointer to something in the I guess on the Ethereum network in some way, and it's this key pair. Basically what you have is a private, like all of these all of the cryptocurrencies, the generic way they work is they have the same key value pairs with it, but you basically have a private key which you never show to anyone, and then you have a public key, which is the one that the world faces, and they see the private key as some something to yourself, and the public key is the world-facing one. And what it's saying here is that this one here is suitable for storing addresses of contracts, so it's the address of a contract, or a hash of the public half of, yeah, okay, fine. So it's basically a hash of the public key pair belonging to the external account. The account I presume that you're going to be sending to. We can click on here and see what external accounts it actually refers to. Okay, it's taking us back to the beginning, I think, or at least something that looks like the beginning. So I'll close it. Oh, it's taken us, we've gone in a circle by the looks of it. Maybe it's taking us further down the page. Anyway, the public automatically generates a function that allows you to write to the current values outside of. So this is, again, we know what public is, outside of the contract. Without this keyword, other contracts have no way to access the variable. So I don't even know if we need to write private, but if we forgot to put, or if we didn't put public in, we just did address minter, I presume it's then going to be private by default. So the external code of the function generated by the compiler is equivalent to the following. Ignore external or view. Okay. The code of the function. Okay. From minter, view address return minter. Okay. You could add a function like the above yourself, but you would have a function and a state variable with the same name. You do not need to do this. The compiler figures it out for you. Okay. Right. The next line, which I had no clue about, the next line, mapping address to unit. Or is that connecting this external address to what this, so not unit, to unsigned integer? So mapping address to unsigned integer of public balances. So, right. Oh, I guess that's the balances actually that's going to be spoken about in the contract. Also creates a public state variable. We see that from public here. But it is a more complex data type. Okay, so we know it's a data type because in Solidity we understand that data types or that variables, so our balance variable, which has been made public, it's going to have a type. It's got to be something, and here we're told that it's of type mapping, I guess. The mapping type addresses. The mapping type maps addresses to unsigned integers. So, okay, that's what it is at least. I guess we'll see, or it'll probably tell us what it means. It as kind of like a way of example. If I could draw a picture of it or something, I've got an idea in my mind at least of what it means. So that it's of this type. And it's kind of like linking this external address to some, I guess, unsigned integer that we can refer to inside of the contract. Mappings can be seen as hash tables, okay, which are virtually initialized. What is a hash table? I'm kind of like thinking Python dictionary straight away, which is this key value pair. Something that, this address is linked to this variable, basically. So mappings can be seen as hash tables, which are virtually initialized, such that every possible key exists from the start and is mapped to a value whose byte representation is all zeros. However, it is neither possible to obtain a list of all the keys of a mapping, nor a list of all of the values. Record what you added to the mapping, or use it in a context that it is not needed. Or even better, keep a list or use a more suitable data type. Okay. The getter function. So did we have a getter function here? No. No, we didn't have anything here, so I'm wondering what this getter function is. Okay, the getter function created by the public. Okay. The getter function created by the public keyword is more complex. In the case of mapping, it looks like this. Okay. Function mapping balances. Okay, we'll see what this all means. We can open some of this in Remix at any point in time. If I guess if I click on it, it will open up a new Remix and kind of like does this thing, which is the integrated development environment. It's doing some stuff. I don't know where to run it at this point in time. I presume if I was to click, everything here is underscored in red. Syntax error. Free functions cannot have visibility. So I don't know why it gave it. I guess it gives you the functionality to launch everything in this Remix integrated development environment. There is, and it looks like you write your code at the top and there's an output somewhere down below, and I guess you could hit the run button, although in this case there's going to be a whole bunch of errors. We already know that there's going to be a bunch of errors because of all of these heavy underlinings everywhere in red. I'm going to close this down because we don't need to have that there. Let's have a look. You can use this function to query the balance of a single account. Okay, fine. The event sent address from address to unit amount declares an event. Okay, there we go. So like, we could click on it and see what event means, but let's just assume we know what it means. So it declares this event, which is emitted in the last line of the function, where it's got a send. Okay, so basically going up here, or is it sent or send? Let's have a look. I guess, is it from, which is emitted in the last line of the function send. Okay. Ethereum clients such as web applications can listen for these events emitted on the blockchain without much cost. As soon as it is emitted, the listener receives the arguments from, to, and amount, which makes it possible to track transactions. So it's kind of, it's really like, it sounds like quite beautiful language in the sense that we're quite very simple, in a nice way of having code that enables you to talk to the blockchain effectively on the Ethereum network. So I mean, maybe it does kind of like, it is deserving of I guess, a language on its own. Could you use another language? I don't even know. That I'll leave that for another video. To try and do it in Python, maybe. Like, can we write to the Ethereum network using Python or using another language? So anyway, I think we get that part of it. To listen for this event, you could use the following JavaScript code, which uses web3.js to create the coin contract. So the coin contract object in any other interface calls the automatically generated balance function from above. So we've got this coin.sent.watch. Okay, this is standard JavaScript, although I forget a lot of my JavaScript because I now code a lot in Python. But this is the callback function error result. It's kind of like the standard callback, I guess. And if there's no error, if not error, then console.log. So write to the console that we've had a coin transfer plus result.args amount. So you either get an error or you have a result. So if not error, you get the results args amount. And then you get the args from, and then you get the args, and then you get the to as well, result args to, and so forth. Okay, and then you get the balances, console.log balances now. So you get the sender balance, coin balances call, and the receiver balance over here next. So that's basically it. Okay, fair enough. Looks relatively clean. I'm not sure why JavaScript needed to be imposed, but I guess you can listen on using JavaScript. The constructor is a special function that is executed during the creation of the contract and cannot be called afterwards. Okay, I think it's like, it really is the equivalent in concept for the constructor of a class. So we've got a constructor of this contract, of a contract. A contract feels like it's got this encapsulation just like class. In this case, it permanently stores the address of the person creating the contract. I guess you can create as many contracts as you like, and each one will have its unique constructor. So it works. It just seems like it works exactly like classes do. So if you're comfortable with classes and object-oriented programming, the constructor is nothing new. The message variable, together with the TX, which I presume stands for transmit and block, is a special. The message variable is a special global variable. So that's what I said. It's one of the keywords, I guess. So it's kind of like what was that message that contains properties which allow access to the blockchain. So this questionable thing that we were asking about in the beginning, saying like I don't know what that is. Message.sender is always the address where the current external function call came from. So it's the sender. So where it's kind of like saying like I don't know where this comes from in the constructor. We're now told down below that message.sender is always the address where the external function call came from. Okay. Functions that make up the contract, and the user contracts are called mint and send. So I guess you mint something and you can send it. I presume that's it. Did we have a mint and a send here? We've got, well, here we've got a mint. Sends an amount of newly created coins. So you mint your coins. Send them out newly. So you mint your coins and then you send your coins at the same time, although the send is here as well. So I'm trying to think. You mint your coins, you've got a receiver who receives it. And then are you sending it from a sender to a receiver? Possibly so. Scroll back down and get more descriptions. Right. The mint function set. Okay, well, anyway, we've got the description. It's going to debunk this here, so there's no point guessing it. The mint function sends an amount of newly created coins to the other address. Okay. The require function. The require function call defines conditions that reverts all changes if not met. Okay. In this example, require message sender equals minter ensures that only the creator of the contract can call mint. Okay, there we go. In general, the creator can mint as many tokens as they like, but at some point this will lead to a phenomenon called overflow. Well, you basically flooded them, because I was kind of like questioning this in my mind as I was reading it, because if you can just keep minting forever, you're going to like effectively you're going to be like a central bank printing money forever, and you'll sort of devalue your currency. I think programmatically, like at some point anyway, like if the number got too big, so you just minted too much, that you would have a proper overflow, like a stack overflow. Note that because of the default checked arithmetic, the transaction would revert if the expression balance receiver plus equals amount overflows, i.e. When balance receiver plus amount in arbitrary position arithmetic is larger than the maximum value of 2 to the power of 256 minus 1, which is this humongous number. Let's just do it. I don't know if I'll even be able to do it on the standard calculator, but 2 to the power of 256 can be this enormous number. There you go. It's 1. So you know you got 77 good zeros. So it's 1. I don't even know what that number is. It's so big. But 1 with times 10 to the power of 77, roughly 77 zeros. It's huge, huge, huge number. But yeah, if you do breach it, then even the Federal Reserve couldn't breach that with dollars. But maybe like if we fractionalize our contracts, they're worth less or something. Maybe you could breach it. This is also true for the statement balances. Receiver plus equals amount in the function send. Okay, errors. I think we're going to kind of like maybe we'll wrap up sort of like down here. Yeah, maybe we'll wrap up kind of like here. We'll have a look at the blockchain basics. The errors part is important. So errors allow you to provide more information to the caller about why a condition or operation failed. Errors are used together with the revert statement. So the revert statement unconditionally aborts and reverts all the changes similar to the require function, but it allows you to provide the name of an error and additional data which will be supplied to the caller and eventually to the front end application or block explorer. So someone's going to get a message and they can see what this error was about so that a failure can be more easily debugged or reacted upon. Okay, let's look at this bit. The send function can be used by anyone who already has some of these coins. Because if you don't have the coins, I guess you'd have to mint the coins. Um, so anyone who's got coins can use the send function to send coins to anyone else. And this is kind of like the convenience of it, I guess, because you're always referencing the coin address. So I guess you can always kind of like keep on the transfer. Everyone can transfer the coins around like a big merry-go-round using this send function. It's beautiful. It's a beautiful piece of code which it's like the digital version of a central bank. Really, it's fantastic. Um, if and it's fantastic in its simplicity because this is how it should be. If the sender does not have enough coins to send, the if condition evaluates to true. As a result, the revert clause will reverts will cause the operation to fail, while providing the sender with error details using the insufficient balance error. So yeah, it's kind of like this warning thing. Note if you use this contract to send coins to an address, you will not see anything when you look at that address on the Blockchain Explorer because a record that you sent coins and changed the balances are only stored in the data storage of this particular contract. By using events, you are creating a Blockchain Explorer that tracks transactions and balances of your new coin, but you have to inspect the coin contract address and not the address of the coin owners. Okay, I need to get my head around that one. Then it's some blockchain basics, which I think that was the introduction to smart contracts. Because I clicked on 3 tabs and I could have sworn one of them might have been the blockchain basics. But anyway, we've come down here and got blockchain basics. Blockchain is a concept. Blockchain is a concept. Blockchains as a concept are not hard to understand for programmers. The reason is that most of the complications are just there to provide a certain set of features and promises for the platform. Once you accept these features as given, you don't have to worry about the underlying technology, or do you have to know about how Amazon's AWS, the Amazon Web Server, works internally in order to use it? Question mark. Okay, yeah, it's kind of like you don't need to know about the mining, hashing, elliptical curve, cryptography, and peer-to-peer networks in order to do this send and receive kind of stuff on the blockchain. We trust that, or not trust. We understand how the blockchain works, and there's some core parts to it that will make it work. Mining is necessary for creating of the coins in the first place. Hashing is necessary for the purpose of the cryptography part of it. This elliptic curve cryptography, which I've seen quite a few times, I kind of want to click on it quickly. Elliptic curve cryptography, ECC, is an approach to public key cryptography based on the algebraic structure of elliptic curves. Okay, we're going to look into all of that. I wonder if there's any nice pictures. Elliptic curve theory for the purpose of this article. No, although I'm just going to say one big global word, which is kind of like security, effectively. but it's far deeper than that. But yeah, we won't. We'll jump out of that for now. Transactions. Okay, a blockchain is a globally shared transactional database. So we effectively, I guess, when we were looking at that piece of code right at the top, and it's like remember where we are by this transactions bit here. Kind of scroll down to like midway through, I guess. But when we were looking at our piece of code, this Ninter piece here, this address public Ninter, I think it's pointing to the public blockchain. Effectively, that's what it's for. And this mapping piece here is kind of like connecting, I guess, the address in some way, like it's recognizing the balances. And then we've got this to and from send thing as well. Let's scroll back down. So blockchain is globally shared transactional database. So we are implementing on the database with our contract. This means that everyone can read entries in the database just by participating in the network. If you want to change something in the database, you have to create a so-called transaction. The funny thing is, databases, if you look at database management systems, they work with transactions effectively. A transaction is a communication to a database. So like inputting one line item into a database is called a transaction. And in regular databases, you can revert back to earlier transactions. I believe the advantage of the blockchain database is that you can't tear up, you can't delete things, so you can't revert to an earlier version of the database, so that errors kind of like a retain. You can correct errors with new transactions, but the log is always stored, so you can't like delete things from the database, so it keeps it honest. So but we always knew this, cryptocurrency is honest compared to other databases which rely on trust of the database administrator, such as like a central bank who can tamper with your money. So this way you can't. The word transaction implies that the change you want to make, assume you want to change two values at the same time, is either not done at all, so this is the important bit, or completely applied. That's the purpose of the transaction. So it either passes into this immutable blockchain because it qualifies to do so, because, for example, the amounts, you didn't have a negative amount or something like that, or it just gets completely, or it doesn't enter the blockchain, and that's it. It keeps it really, really honest and really clean. Furthermore, whilst your transaction is being applied to the database, no other transaction can alter it, because that's the other thing. Can you like get a double entry at the same point in time? That's prevented as well. As an example, imagine a table that lists balances of all accounts in an electronic currency. If a transfer from one account to another is requested, the transactional nature of the database ensures that if the amount is subtracted from one account, it is always added to the other one, right? No errors can happen, no theft can happen, no double ledgers, none of that kind of stuff can happen. It's completely secure in this way. So it either fails, in which case the transaction doesn't happen for the purpose of the sender and receiver, or the buyer and the seller, however you want to consider, or the transaction does happen for both parties. If due to whatever reason adding the amount to the target account is not possible, the source account is also not modified. He's repeated this multiple times, and it's really important to understand this. It is the essence of the blockchain and transactions in the crypto space. It's much more honest than the fiat system, where you can modify things. Here you just can't. The fiat system kind of like trusts that we do these things, but what we have to do in the fiat system from time to time is reconcile to make sure that our databases match. And then you can have an argument about where they didn't match. In this case, they literally must match, because you don't permit anything else to happen. So the transaction doesn't proceed if they can't match. Furthermore, a transaction is always cryptographically signed by the sender. So that's an additional layer of the security. The sender is called the creator. This makes it straightforward to guard against specific modifications of the database. In the example of the electronic currency, a simple check ensures that only the person holding the keys to the account can transfer some compensation, e.g. Ether, from it. Okay. Blocks. One major obstacle to overcome is what in Bitcoin terms is called a double spend attack. Okay, that's what I was referring to earlier. Actually, what happens if two transactions exist in a network that both want to empty an account? Only one of the transactions can be valid. Typically, the one that is accepted first, so the first one on the blockchain. The problem is that first is not an objective term in the peer-to-peer network, and I think that's because you broadcast something to the network, and the one that is I presume that the first one is the first one that's accepted by the consensus of the community. So you might have broadcasted two things simultaneously, or even A before B, but B might be the accepted one. So even though B was sent second, it might be the first one to be accepted. So we just got to be aware of that. The abstract answer to this is that you do not have to care. A globally accepted order of the transactions will be selected for you, solving this conflict. The transactions will be bundled into what is called a block, and then they will be executed and distributed amongst all the participating nodes. If two transactions contradict each other, the one that ends up being second will be rejected and not become part of the block. So you can't get this double spend attack. One of them is literally thrown out. These blocks form a linear sequence in time, and that is where the word blockchain derives from. The blocks are added to a chain at certain regular intervals. For Bitcoin, I believe it's 6 minutes, although these intervals may be subject to change in the future. For the most up-to-date information, it is recommended to monitor the network. For example, on Etherscan. So for Ethereum, we go to Etherscan, and we can see this beautiful little thing over here. And Ethereum average block time chart. Okay, is that every 15 minutes? Every 10 or 15 minutes? It looks like at some point maybe there was a lot of stuff that was going on the network. So the blocking time series became a bit longer. I guess there are periods of demand. And there's a whole bunch of other things to take a look at on that. As part of the order selection mechanism, which is called mining, it may happen that blocks are reverted from time to time, but only the tip of a chain. So basically you can only return kind of like the last block effectively. You can't sort of like go and unwind previous things in the block. The more blocks are added on top of a particular block, the less likely this block will be reverted, because you can't do it. Like, it just becomes harder and harder to go and do the unwinding because the community has accepted all of these other blocks, so the transaction's been accepted. So it might be that your transactions are reverted. And either removed from the blockchain, but the longer you wait, the less likely it will be. So it's kind of like the acceptance begins to get settled, and that's it. Transactions are not guaranteed to be included in the next block or any specific future block, since it's not up to the submitter of a transaction, but up to the miners, which is kind of like the community, I guess, who are solving for this, to determine in which block the transaction is included. If you want to schedule further calls of your contract, you can use a smart contract automation tool or an Oracle service. Now, the thing about this is when you do broadcast to the blockchain, you kind of like pay a fee to do it. And if you kind of like want more guarantee that this happens, you make your fee a little bit higher. If you don't care so much because it's a lightweight transaction and you don't mind waiting a little bit longer for your transaction to complete, then you pay a smaller fee. So it's a very, very fair system. I guess finally, the Ethereum virtual machine, I'm just going to read the overview of this because I'm not really sure what the Ethereum virtual machine is, although is that like the JavaScript or Node runs on some sort of virtual machine. The Ethereum virtual machine is a runtime environment for smart contracts in Ethereum. It is only sandboxed. It is not only sandboxed, but actually completely isolated, which means that code running inside the Ethereum virtual machine has no access to the network, file system, or other processes. Smart contracts have limited access to other smart contracts. Okay. So basically, the Ethereum virtual machine is a runtime environment for smart contracts in Ethereum. There are two types of accounts in Ethereum which share the same address: external accounts that are controlled by public-private key pairs, i.e. humans, and contract accounts which are controlled by the code stored together with the account. So the public-private key, which us humans have, I guess it's going to differ from the contract thing, which I guess presumably automatically gets triggered. The address of the external account is determined from the public key, while the address of a contract is determined at the time of the contract and the time the contract is created. It's derived from the creator address and the number of transactions sent from the address, the so-called nonce. Okay. Regardless of whether or not the account stores code, two types are treated equally. The two types are treated equally by the EVM. Okay. Every account has a persistent key storage mapping, 256-bit words to 256-bit words called storage. Furthermore, every transaction has a balance in ether, in way to be exact. So we've got this thing, 1 ether is 10 to the power of 18 ways of like an ether is broken down to minute parts, which means that, I don't know, it's got like tiny little denominations. I think an ether, 1 Ethereum is basically like a couple of $1,000. So a way, which is one like fraction of an ether, is a fraction of a dollar basically, which can be modified and sent by including an ether. I guess I'll leave the rest. I might bring it to an end because this is more about cryptocurrencies at this point rather than the code. But I think if I do the next video, I'm going to try and actually move it into the code and kind of like try this remix integrated development environment and try and maybe create a function or call a function or do something in some way. But it looks like whatever we're doing on the Solidity platform isn't kind of like the same as when we sort of like do it in Python and you run it on your you run it in your Visual Studio Code or whatever your integrated development environment is, and you sort of like use a Jupyter notebook and you get a chart out. It's not designed for that. The Solidity language looks like it's designed to interact, purely with the Ethereum network. It's not a general purpose programming language, at least from what we've seen on this. And at that point, I guess I might sign off. So we'll take another look at some point. We've done the blog and the documentation. Maybe we'll sort of like look at use cases or do some code in a later section. Gaming in virtual worlds, that looks really interesting. There's loads of fun things. Decentralized finance, which is known as DeFi, everything gets given this fancy acronym. Non-fungible tokens, NFTs, something that was very popular. A really useful feature, by the way, of kind of like keeping digital assets unique, nearly like a signature or an autograph. So those types of things. I guess it gives us access to all of those new things that are up and coming and being developed on the Ethereum network. So that's pretty much it. I go back to the original page, and that's Solidity, our code-based language that is used for developing smart contracts that run on Ethereum. And that's the end of in our Python coding session, but today it was on Solidity. If you like this, click the like button, follow. I should have said that right in the beginning. Forward it on to other people, stick it into social networks and all the rest of it, and follow once more If you could follow twice on the second account, even better. And that's it. And if you have any questions or comments or any points that you want to raise or anything that looked erroneous at any point of the description that I gave, add that on as well. So that's the end of Solidity, the Solidity introduction for newbies like myself.